Welcome to our in-depth tutorial on using elliptic curve cryptography, or ECC, to build secure cryptocurrency wallets. In today's digital age, ensuring the security of your digital assets is more important than ever. If you're interested in understanding how ECC works and how to implement it in Java for wallet creation, you've come to the right place. First, let's discuss what elliptic curve cryptography actually is. ECC is a type of public key cryptography based on the algebraic structure of elliptic curves over finite fields. It offers a higher level of security with smaller key sizes compared to traditional cryptographic techniques like RSA. Now, why should we use ECC for cryptocurrency wallets? A cryptocurrency wallet stores the private keys needed to access the funds in blockchain networks. Using ECC allows wallets to provide strong security with less computational overhead. This is particularly valuable for mobile and embedded systems. To demonstrate this, we'll be creating a simple cryptocurrency wallet in Java utilizing ECC. We'll cover key generation, address creation, and signing transactions. Let's start by ensuring we have the necessary libraries. We will be using Bouncy Castle, a popular library for cryptographic operations in Java. Now let's set up our project and import the required libraries. Create a new Java class called Wallet and add the necessary imports. Now we need to add the Bouncy Castle security provider to the security context. This allows us to use Bouncy Castle's cryptographic features throughout our application. Next, let's create a method to generate a key pair. A key pair consists of a private key and a public key, which are crucial for our wallet functionality. Let's add a main method to test our key pair generation. We will generate the keys and print them to the console. Now let's run our project. If set up correctly, you should see the private key and public key printed in the console. Each key is essential for our wallet's operation. Next, we need to create a method to generate a wallet address from the public key. Wallet addresses are typically a hashed version of the public key to create a shorter, more manageable identifier. For simplicity, we will return the base 64 encoded public key as the wallet address for now. Keep in mind that in real applications, you'll want to use more robust hashing and encoding techniques. Let's run our application again to see the wallet address generated. Keep in mind that in real scenarios, the wallet address will be derived from digest algorithms, not directly from the public key. Now that we have our keys and wallet address, the next crucial aspect of our wallets is the ability to sign transactions. This is done using the private key. Signing ensures that transactions are authorized and can be verified by others. We are defining a method to sign transactions. The transaction data represents the transaction details, and we will use the private key for signing. Note the signature algorithm SHA-256 with ECDSA, which is standard for ECC transactions. After executing this code, you will find the transaction signature printed. This signature can later be used to verify that the transaction was indeed signed by the holder of the private key. To verify a signature, we will create a verification method in our wallet class. This method will check whether the provided signature was generated by the corresponding private key for the given transaction data. Now we can use this verification method to check the legitimacy of our signed transaction. When you run this code, the output should indicate whether the signature is valid. This completes our basic implementation of a wallet utilizing elliptic curve cryptography. Before we finish, let's summarize what we've done. We have created a Java application that can generate key pairs, derive a wallet address from the public key, sign transactions with the private key, and verify those signatures using the public key. This is a simplified version of how cryptocurrency wallets work under the hood. In practice, you'll need to consider additional security measures such as encrypting private keys, using secure storage, and managing multiple keys. I recommend exploring the Bouncy Castle documentation for more advanced features, including key storage options and more robust encryption techniques. Always keep security considerations at the forefront when building cryptographic applications. Thank you for watching this tutorial on elliptic curve cryptography for cryptocurrency wallets. If you found the content useful, please like, share, and subscribe for more programming tutorials. Don't hesitate to leave comments or questions below.